Welcome to Physics 2212, Lab 4, Bar Magnets, by me. Yay. The introduction. For the purpose of this lab, we measured the distance between the distance of the magnetic field due to a small bar magnet using a phone. The model for this was a physical magnet in the laboratory, as well as a phone using an app and a magnetometer inside the phone. We also used GlowScript to model this afterwards. The results of this were we found n to be negative 1.883. The main physical principles used in this were Biot-Savart law, which states that the magnetic field produced by a current carrying wire given by current distance and orientation. Basically, this is shown by the equation in the top right, which is B is equal to mu 0 over 4 pi times q v times r hat over r squared. The other main law was magnetic field of a dipole, which states that the formula to find the magnetic field of a dipole is Br is equal to mu naught over 4 pi r cubed times 3 times mu times r hat minus mu. For the experiment, we were in the laboratory and we had two different setups. For each setup, we used the magnetometer on the phone using the Firefox app, and we measured the strength of the field at different distances, and we plotted that data in Excel. We lined the phone up in perpendicular to mitigate the Earth's magnetic field affecting the magnetometer in the phone. So as you can see in the diagram on the left, we put tape on the phone to identify the magnetometer, and then we measured distances and measured the recordings on the phone at each distance. You can see that in action in the image in the top right. So here's our data. If you look at the graph, you can see that there's a graph of the magnetic field versus distance. And as you can see, there's a negative trend in the data, which shows that the magnetic field is inverse to distance. So the closer you are, the stronger magnetic field. The farther you are, the weaker the magnetic field. And here's all the data we used to get these numbers on these sides. For the coding portion of this, we had to create a function of the dipole, as seen here, and then we had to make a lot of arrows. One would say too many arrows, I think. And then displayed, it's all this. As you can see, the blue is the magnetic field at perpendicular. Orange is going to be parallel, and purple is the rest. Some possible errors we may have encountered in this lab were we treated bar magnets as dipoles. That was just an assumption we used to simplify it. And we also assumed the magnetic field falls off as distance increases, which we actually did find to be true, maybe not linearly. Some errors in the lab were other objects nearby may have skewed the data or magnetometer, such as other magnets, other electronic devices, the table itself, they all could have impacted it. And the location of the magnetometer was not fully accurate when we marked it with the tape on the phone. It was very difficult and challenging to get that, and we had to do it several times, and even the TA struggled in the end. Final discussion. What if? What if you hadn't oriented your experiment to compensate for magnetic north, and instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your result have changed? My answer to this was the Earth's magnetic field would interfere with the bar magnet's magnetic field, which would mess up the results. What if you were to stick two identical magnets together, end and run the experiment again? How would you expect your measurements to differ? I responded, the magnetic field's magnitude would be double, and the direction of it would remain the same. Direction would not change. Thank you for watching. Give a like and subscribe, and 100. Thanks for stopping by.